Welcome to your video lesson, combination of sample spaces and the fundamental counting principle. So you are going to be able to find the sample spaces and know what that word means in vocabulary for probabilities, and then you're also going to be able to use the fundamental counting principle to quickly determine the total number of possible outcomes of an event or combination of events. So your vocab words are sample space, tree diagram, and, whoopsie, that fundamental counting principle. I'll abbreviate. So, looking at this, finding the sample space. So a sample space is going to be the set of all of the possible outcomes in a probability experiment. So all of the possible outcomes that could happen. So if you're looking at ice cream, a vendor sells vanilla and chocolate ice cream. Customers can choose from a waffle or sugar cone, and they can either get hot fudge or caramel. So the sample space is going to be all of the possible different order combinations that could come up from one scoop of ice cream, a cone, and one topping. So one way to do this is that you could make a table. So we could say that I'm going to get vanilla ice cream in a waffle cone with hot fudge. I'm going to get vanilla ice cream with a waffle cone but caramel instead. Vanilla, sugar cone, hot fudge, vanilla, sugar, caramel. So notice all of these are different outcomes. With chocolate, I could get waffle, hot fudge. Chocolate could be waffle, then caramel. Chocolate could be sugar, then hot fudge. Or chocolate could be sugar, then caramel. So what I notice is that there's 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes all together. And this table, what's nice about the table is that it gives me a visual of what different possible orders would look like, what their flavor would be, what type of cone, and the hot fudge. Instead of just knowing it's 8, I know exactly what those 8 are when I make a table. So that's the benefit here it's pretty easy to make a table. So we'll try to make a table on our own now. If there's an animal shelter and they have both male and female Labradors, and then they are in yellow, brown, or black, we could find the sample space or the total possible outcomes of Labradors that would be available at this shelter. So what I can do is I might start with male or female. So I could have a male that is yellow. I could have a male that is brown and a male that is black. I could also have a female that's yellow, a female that's brown, and a female that's black. Miss Simmers has had one of these named Mandy, one of these named Jack, one of these named Tanner, and now one of these named Buddy. So that's kind of fun. So that just shows that there are 1, 2, 3, 4, 5, 6 possible outcomes for what kind of dog, what gender, and what color you could get at this shelter. Okay, so that visual just gives me an idea of the gender and the color options I have. Another way to do this is to make a tree diagram. It's called a tree diagram because you kind of start with branches and those branches go on. So one example of that, if we have this question of cars, so we have that a car comes in silver, red, or purple, and it could be a convertible or a hardtop. So what I would write down, I start with my branches. Maybe I start with just my color. So this is one event in this probability, and the color could be silver, red, or purple. You gotta kind of be neat with these. This can get messy. If it's silver, my second event is the style, convertible, or hardtop. So if it's silver, it could be a convertible, or it could be a hardtop. If it's red, it could be a convertible or a hardtop. Purple could also be a convertible or a hardtop. So what those branches do is they allow me to see that I have 1, 2, 3, 4, 5, 6 possible outcomes. So again, it's like the table, but again, it lets us see what the options are, not just the number of them. So I could have a silver convertible, a silver hardtop, red convertible, red hardtop, purple convertible, or purple hardtop. So it gives me a very clear picture of what the options are. At a deli, so this has a little bit more choices. At a deli, I can choose from the salad bar, wing bar, soup bar. I could get a bun or breadstick, And then for dessert, I could either get a pudding or a slice of pie. So I'm wondering what are the combinations of meal outcomes that I could have. So I start with maybe my main course is one option, and that's salad. I forgot, I'll put soup next, and then wing. Did that out of order. After I pick my main dish, I also get to pick a bread option. So with the salad, if I pick salad, I could still get a bun, and I could still get a breadstick. Soup, I could get a bun and a breadstick. Wings, I could get a bun and a breadstick. And then my third option to make my meal complete is dessert. So I could get a salad, bun, and then I could choose from pudding or pie. So with each of these, I still have those two options. So it gets a little bit messy if you're not neat, kind of like me with the stylist. For each option, I have two more dessert options. So you can see my list of outcomes is becoming a little bit longer because of all the variation and choices that I have. So for each of these, I have the pudding and pie option. So at the end, I can count those up. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 possible outcomes for food options. I won't list them all, but as you can see, I could have a salad with a bun and pudding. I could have a salad with a bun and pie. I could have a salad with breadstick pudding or a salad breadstick pie. So you can see that those branches just keep going off the more choices that I have. So finding the probability then of an event is kind of a little bit different now. A little change of gears, and then we'll talk about something that makes this even easier. So with a fair game is one in which each player has an equal chance of winning. So that'd be 50-50. So for example, if Marco tosses 3 coins and all 3 coins show up heads, Marco wins. Otherwise, Cara wins. Find the sample space, then the probability that Marco wins. So 3 coins. So we know that the first event is the first coin. So the first options are heads and tails. The second event would be tossing a coin again, and you can still get heads or tails, and that could happen for either first event. The third then, again, we can get heads or tails for each event that happened before that. So I write my events, and then what could happen, outcomes after that. So what I notice is that I have 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes, but we're wondering, so that's our sample space, 8 possible outcomes, but what's the probability that Mark wins? Well, Mark wins is if all of them are heads. So this is only one, heads, heads, heads. That's only one of the 8 options. So this is not a fair game because Marcos only has 1 in 8 chance of winning, whereas Cara then would have the other 7/8 chance that he doesn't get all heads. So one thing to make this easier, which I know all of you love, writing less, so let's show you really jazzed up about this option. It's called the fundamental counting principle. So it just means that you can multiply the outcomes for each event together, and that'll give you the total. So for example, if we're looking for the total number of outcomes, if a coin is tossed and a number cube is rolled, well, you think a coin is tossed, and for a coin, I have 2 outcomes, heads and tails. So that's 2. For a number cube, I have 1, 2, 3, 4, 5, and 6. So that's 6 possible outcomes. So fundamental counting principle is there are 12 outcomes for those 2 events to happen together. And you could see that in a tree diagram. So this fundamental counting principle is nice if you just want to know the sample space, if you just want to know the possible number. But it's not nice to know the exact combinations you could have. A tree diagram would be better because then I could say, okay, I can have heads and a 1, 2, 3, 4, 5, or 6. And I could have tails and a 1, 2, 3, 4, 5, or 6. So we just, different variations of what you're looking for will depend on which strategy you use. So there's a couple here, and then you're on your way. So if we find the total number of outcomes for choosing from bike helmets, that come in 3 colors and 2 styles. So these are events, the colors and the style. So 3 colors times 2 styles means that we have 6 possible outcomes of helmets. Quick and easy. Last one for jeans. The jeans shop is selling young men's jeans in different sizes, styles, and lengths, and that's shown here in this image. We want to find the number of jeans available, the sample space, and then find the probability of selecting 32, 34 slim fit. So we notice waist size, this is one event. We have 1, 2, 3, 4, 5 times 1, 2, 3 in length, and then 3 different styles. So this fundamental counting principle is going to be easier when there's more events, because you realize we're really doing 15 times 3, which is 45 different options for jeans. And that would be a really messy tree diagram. So this is where that's helpful. Then we can find the probability of having a 32, 34 slim fit. That's going to be one of the 45. So someone that buys those is one of the 45 options that are available. All right, that's it. Probability is pretty cool because we're using it all the time, whether we know it or not. Maybe try to find some ways that you use this, or next time you go to a restaurant, kind of look at the menu and decide if you can find out the total different possible meal combinations. See you soon.